Welcome to the course on computer design of electrical machines. We'll have a lecture 15 today on design of three-phase induction motor part 4. This we start from introduction, then we will like to go to complete design example 2, then numerical exercise and problems. Then that we will have in typically some subjective problems and some solved example followed by references. So coming to typically an analytical example of complete induction motor design. Start with like design a 11 kilowatt 3-phase 440 volt 50 Hz 1000 RPM synchronous speed squirrel cage induction motor having a full load efficiency of 0.86 and power factor of 0.86. The temperature is not to exceed 50 degrees centigrade. Assume suitable and justified value for various design data. Now discuss about solution. For the estimation of main dimensions, we have to go to the calculation of the output equation. So first we have to calculate the synchronous speed which is required in this. That is ns 120 f by p. So that's ns upon 60. So it comes in rps. It comes 16.67 rps. And number of poles from here we can find out 2 f upon ns, that comes around 6. So considering the B average of 0.45 Weber per meter square and the electrical loading AC 22,000 ampere per meter and winding factor of 0.955, which is well valid for saying double layer winding with the winding distribution of 60 degree phase spread and typically the phase factor of around 1. Now coming to kVA input Q, that is equal to P0 on efficiency into power factor. So putting value of 11 divided by 0.86 into 0.6, this comes 14.9 kVA. Now for the output equation, we have output coefficient C0 equal to 1.11 pi square kW BAB into AC. So it comes after putting value 104, and D square product from this output equation, D square L is Q0 Q upon C0 N L NS, and putting this value it comes 8.6 into 10 power minus 3 meter cube. So for a good power factor, of course we have to consider the another equation for calculating the main dimensions L and D. So one relation of course we got from output equation D square L. For second relation, there are number of criteria. Here we are considering for a good power factor L upon tau should be 1 to 1.25. So considering the L upon tau equal to 1, it gives overall good electrical design induction motor. So taking L upon tau equal to L upon pi d by 6, that is 1. So it comes L equal to, another relation comes L equal to 0.523 D. So it putting the value, so here D comes 0.254 meter and L comes 0.14 meter. Now coming to the calculation of stator design. So for stator design, first we go to the stator voltage per phase. Each phase is given for delta star with the starter. So finally winding is supposed to be in delta connection. So phase voltage equal to same line voltage, that's ES equal to 440 volt. And now we can calculate typically the flux, maximum flux per pole, that comes B average tau into L. So it comes putting a value of B average NL, it comes 8.25 into 10 power minus 3 Weber, and from this we can calculate the now stator turns per phase, TS equal to ES upon 4.44 F 5 M into KW. So it comes 250 turns with the round off, and taking the slot per pole per phase for stator QS equal to 3. So slot stator total stator slot comes M equal to QS into P. So it comes 3 into 3 into 6, that's 54. Now we can calculate the slot pitch, that is YSS equal to pi d divided by number of slots. So putting value it comes 14.5 millimeter, and total number of conductors now we can calculate 6 into TS. So it's a 3 phase into the typically 3, and in each turn there are 2 turns, so it becomes 6 TS for 3 phase winding. So that comes 6 into 250, that's come 1500. So conductor per slot we can round off, that is ZSS equal to 15 upon 54, it comes 28 as a round off. And now we can of course retrieve back again to get the total number of turns. Now D equal to 0.25 meter and L equal to 0.14 as we got from output equation. So tau is 0.131 meter. So length of the core is now 140 millimeter, and therefore one radial ventilating duct of 10 millimeter in width is provided, considering of stacking factor of laminations of 0.9. So net iron length is Li equal to K into L minus NdWd, that comes typically 0.117 meter or 11.7 centimeter or 117 millimeter is the now net iron length. And lamination of alloy steel of 0.5 mm thickness are considered here. Coming to now stator design, so slot winding, stator winding is delta connected in order to the machine may be started by star delta starter, and now stator voltage is equal to 440. So total number of that stator conductor we got it. So number of slot conductor per slot is say 1528, and total number conductor ZSH into SS it comes like 28 into 54, so 1512, and stator turn per phase comes TS equal to ZSH into SS upon 2M, so it comes 252. So number of conductor used is very near to the calculated value, and therefore the value of the flux density need to be modified. So here we use the mass winding in parallel sided semi-closed slot. So coil span is CS equal to slot per pole phase, SS bound P, it comes 9. So there is an odd number and allowed for pill pitch coil, so pitch factor is 1. So now with the pitch factor of 1, and so distribution factor is sin sigma upon Q sin sigma by 2Q. So putting the values into here with the 60 degree phase split, so it comes 0.96, and stator winding factor comes KD into KP, it comes 0.96 into 1 to 0.96. And now conductor size, stator current per phase is IS equal to P upon 3 into ES into PF into efficiency, so it comes 11.25 ampere, and taking current density of 4 ampere per meter square. So area of conductor is IS upon JS, so it comes 11.25 divided by 4, so it comes 2.81 millimeter square. Now chosen to use two conductor of 1.4 millimeter bare in parallel. So diameter of insulated conductor is 1.505 millimeter, and area of insulated conductor is AS equal to 2 pi d by 4. So it comes like putting value 3.08 millimeter square. Now coming to finding out slot dimension. Now each conductor consists of two wires outside diameter 1.505 millimeter in parallel. So there are 28 conductor per slot, therefore there are 56 wires in a slot. So now looking the geometry that we have parallel slot, and all dimensions are given here according to the calculation, and we have typically the slot width of WHS 8.4 millimeter by adding the 4 layers of typically the conductors and slot lining, 2 into 0.5, and slot slackness of 1.48, so it comes slot width about WSS 8.50 millimeter. Similarly, we can have a slot depth, for finding typically from 14, typically wires of 14 into 1.505, and slot line 3 into 0.5, and wedge of 3 millimeter, lip of 1 millimeter, and slack etc. equal to 2.43. So at totaling, the depth of the slot becomes DSS equal to 29 millimeter, as you can see in the diagram. Now coming to typically now for further design of stator, before proceeding further, the flux density at a section having a minimum width of 2 must be checked. So slot pitch at typically at A, that is at cross section of narrow end, it comes W2 equal to slot pitch minus slot width. So it comes 15 minus 8.5 millimeter. So W2 is 6.5 millimeter. So flux density in the at this ATT, it comes 5 upon SP up into W2 into Li. So putting the value, it comes with TTA equal to 1.21 Tesla. So this is within the limit of less than typically order of around 1.8 Tesla. Now the dimension of stator slot. So width of the slot is WSS equal to 9.5 millimeter, as we got it, and depth we calculate 29 millimeter. So now we can find out the min turn length. LNTS will be equal to 12 plus 2.3 top plus 0.24 meter. So putting the value, it comes 0.82 meter. And now finding out for the calculation of stator core, the flux in the core is 5 pole by 2. So putting the value, it comes 4.125 into 10 power minus 3 Weber. And considering the flux density of 1.2 Tesla for the core, so area of the stator core is ACS equal to 5 core upon B core, and putting the value, it comes 3.54 into 10 power minus 3 meter square. So now coming to depth of the core, DCS equal to ACS into Li. Putting the value, it comes like a 30.3 into 10 power minus 3, that comes 30.3 millimeter. And outside diameter of the stator laminations, DO equal to D plus 2 DCS plus DSS, so it comes 368 millimeter. And the rotor design, that's air gap equal to length of air gap equal to LG in equal to 0.2 plus under root 2 DLM Putting the value, it comes 0.55 mm, and diameter of the rotor is dr equal to dl minus 2lg, so it comes like a 250 minus 2 into 0.55, it comes 243.9 millimeter. Now coming to typically rotor design. So now for the rotor slot, the number of rotor slots is chosen such that the smooth starting and accelerating condition are obtained. This is secured by adopting one slot less than one slot more per pole pair in the rotor than the stator. So taking a rotor slot, a pair of poles more than the stator, the number of rotor slot will be SR equal to SS plus Q by 2. So it comes like 56 by plus 6 by 2 equal to 57. And the rotor slot pitch y SR equal to pi d minus 2lg upon SR. So it comes 13.7 millimeter. Now coming to calculation of rotor bars. So current in each rotor bar is IB equal to 2m k omega TS upon SR into IS into cos phi. So putting the value, it comes 250 ampere. And considering the current density of 5 ampere per millimeter square in the rotor bar because of better cooling. So area of bar comes AB equal to IB upon JB, that's a 250 upon 5, that's a 50 millimeter square. So a rotor bar of 5 millimeter wide and 10 meter deep is considered here to take care of the area of 50 millimeter square. Now coming to calculation of complete rotor design. So area of the bar used is 50 meter square with the dimensions of 10 into 5. So dimensions of the rotor slot are WS width is WSR equal to 6 millimeter and depth is DSR 13 millimeter for even providing the clearance for die casting. So before proceeding further, the flux density at the root of the rotor teeth must be assessed to take care that it is not exceeding a limit. So slot pitch at the root of the width equal to pi dr minus 2 DSR upon SR. Putting value, it comes 12.3 millimeter, and tooth width at the root of the teeth is W2 equal to slot width minus WSR, so it comes like 6.3 millimeter. So now flux density at the root of the teeth is pi upon SR upon P into L into W2, so it comes around 1.18 Tesla. This is within the limit, and therefore MF required for the rotor teeth will not excessive. So bar are skewed one slot pitch. So extending the bar about 20 millimeter beyond the core length on each side by taking 10 millimeter increase in the length of 4 screwing. The length of each bar will be with the screw LB equal to LR plus 2 into 20 plus 10. So it comes 190 millimeter or 0.19 meter. Resistance of each bar RB equal to P rho CU LB upon AB. So it comes 80 into 10 power minus 6 ohm. And the total copper loss in the bar will be your PV equal to SR IB square RB. So it comes 285 watt. Now coming to the end ring calculation, so end ring current is I equal to SR upon IB into pi B. Putting value, it comes 755 ampere, and taking current density of 5 ampere per millimeter. So area end of ring is A equal to I upon J, so it comes 151 millimeter square. So using an end ring of depth of 15 into 10 section, so depth of the ring is D equal to 15 millimeter and thickness of T equal to 10 millimeter, and area of the ring provided A equal to D into T, that's a 150 millimeter square, and mean diameter of the end ring, that's a D equal to 209 millimeter, so or 0.209 meter. So resistance of each end ring rho equal to rho Cu, R equal to rho Cu D upon A. Putting the value, it comes 92 into 10 power minus 6 ohm. Now copper loss in the two end ring or winding loss in the two end ring is rho P equal to 2 into I square Re. Putting a value, it comes 105 watt. And total winding loss in the rotor, it's a PB plus PE equal to 285 plus 105 390 watt, and we have here rotor winding loss divided by output S upon 1 minus S, and giving the value that from here S upon 1 minus S, the rotor typically we can find out the full load slip from this relation. So depth of the rotor core is taken equal to now rotor core. Now depth of the rotor core to that of stator core, the area of the flux density in the rotor core same as the stator core. So depth of the rotor core DCR equal to 30 millimeter, and in the diameter of rotor lamination DR equal to DSR minus 2 DCR, it comes 0.163 millimeter. It's a 0.163 meter. Now coming to the calculation of parameters, I mean, these were the dimensions. Now we can calculate the parameters. Typically the no load current. So first coming to the magnetizing for calculation, there are two parts of the no load current. One is the magnetizing current, another is the loss component of current. So coming to magnetizing current, the MF required for various parts of magnetic circuit are calculated here. First, taking a air gap. So for stator slot opening, W upon the gap length equal to 3 upon 0.55, that's a 5.45, and for corresponding to this ratio, the Carter coefficient comes 0.63. So gap contraction factor for stator slot is KGSS equal to YSS upon YSS minus KCS into W0, so it comes 1.15. And for rotor slot opening upon gap length is 2 upon 0.55, so this comes like a 3.64. And now MF required for various part of magnetic circuit we can calculate here. For rotor slot opening upon gap length 2.3, so corresponding Carter coefficient is 0.51, and gap contraction factor KGSR equal to YSR upon YSN KCR into, so it comes 1.08. So gap contraction for so slot comes KGS equal to KGSS into KGSR, so it comes 1.242, and now ratio of duct width to half the gap length, it comes 36.4. So now corresponding to this ratio of 36.4, we have a Carter coefficient of 0.9, and gap contraction factor for duct KGD comes L upon L minus ND WD KCD, putting value it comes 1.07, and total gap contraction is Kg equal to KGS into KGD, so it comes like 1.33, and effective length of air gap now LGS equal to Kg into LG, so it comes around 0.732 millimeter. The flux density in the air gap at 60 degree form interpolar axis is BG 60 equal to 1.36 B average, so it comes like a 0.612 Tesla, and MF for air gap ATG equal to 18 to 10 power 5 into BG60 LGS, putting value it comes 375 ampere. Now for coming to MF calculation for stator teeth, the width of stator teeth at 1/3 height of the narrow end, it comes W at 1/3, so putting value pi d plus 2 DSS by 3 divided by SS minus WT, so it comes 7.15 millimeter. And the area of the teeth per pole at 1/3 of height ATS 1/3 SP SS upon P into WH3 into Li, so putting value it comes 7.53 10 to power minus 3 meter square. So flux density BTS 1/3 comes here pi upon ATS, so putting value what it comes 1.95 Weber per meter square or Tesla. So now coming to the calculation of MF for stator teeth. So for stator teeth is BTS 60 equal to 1.36 into BTS 1/3, so it comes 1.4892 Tesla, and corresponding to this flux density, the per unit MF comes ATS equal to 900 ampere per meter, and MF required for stator teeth ATS equal to ATS into DCS, that comes 27 ampere. And now for stator core, area of the core is your ACS equal to DCS into Li, so it comes 35.1 10 power minus 3 meter square, and flux density in the core is BCS pi upon ACS, so it comes 1.17 Weber per meter square, and corresponding to this flux density per unit MF AG or ATCS comes 280 ampere per meter. So calculating the length of the magnetic circuit part in stator core, LCS equal to pi into D plus DSS plus DCS by 3P, and calculating LCS from this relation comes 59 to 10 power minus 3. So MF required for stator core comes capital ATCS equal to small ATCS into LCS, so putting value it comes 17 ampere. Now coming to MF calculation for rotor teeth, the width of the rotor teeth at 1/3 height from narrow end is a WTS equal to pi in bracket pi D minus 4 SR by SR into WTR, putting value it comes 6.75 millimeter. Now coming to calculation of MF for rotor teeth, so WTR is 6.75 millimeter. The area of the teeth is ATR into SR upon P into Li into WTR, so it comes 7.5 into 10 power minus 3 meter square. So flux density rotor teeth at 1/3 height is BDR pi upon ATR, so putting value it comes 1.1 Tesla, and corresponding per unit MF for this flux density from magnetization characteristic of material comes small ATR equal to 900 ampere per meter. MF required for rotor teeth ATR capital ATR equal to ATR into DSR, so putting value it comes 12 ampere. Now coming to MF calculation for rotor core, from the previous calculation we have area of the core equal to ACR equal to 3.15 into 10 power minus 3 meter square, and flux density rotor core is ACR equal to 1.175 Tesla, and per meter ATCR equal to 80 ampere, and length of magnetizing path in rotor core LCR equal to pi in bracket D minus 2 DSR minus DCR by 3P, putting value it comes 34 mm. MF required for rotor core is capital ATCR equal to small ATCR into LCR, so it comes around 9 ampere. Now calculating total magnetizing current for all 5 parts of magnetic circuit with the starting air gap, stator teeth, stator core, rotor teeth and rotor core, with the area here, length here and flux density here, and B60 flux density at 50 degree, and the per unit MF and then total MF. So total MF comes 86 equal to 422, and magnetizing current per phase IM equal to 0.427 P into 8060 by kWs into TS. Putting value, it comes 4.47 ampere. Now coming to second component of no load current, that's a loss component. For calculation of this, we have here the mean width of the stator teeth WS equal to 7.75 millimeter, and width of the stator teeth KGS equal to SS into DSS into WTS into L into sigma iron. So putting the value, it comes 10.8 kg, and the maximum flux density in the teeth 1/3 height pi by 2 into BTS, it comes 1.72 Tesla. So corresponding to this, specific iron loss is 11 watt per kg. So now the iron loss in teeth is KGS into typically specific iron loss. So putting the value of this, it comes 120 watt, and mean periphery of stator core pi d minus pi CS is 1.06 meter. The flux density in your core is 1.175, and corresponding iron loss per unit is per unit weight is 4.8 watt per kg. Now the iron loss in stator core is, weight this specific weight into weight, so that 28.2 into 4.8, 135 watt, and the total iron loss in the teeth and core is 120 plus 135 to 55 watt, and the actual iron loss is about 2 times the total iron loss is 510 watt. So friction weightage loss is 1% of this, so it's 110 watt. So total load loss is 510 plus 110, 620 watt. The loss component of no load current is IL equal to total no loss divided by 3S, so it comes 0.47 ampere. The load current is I0 equal to under root 4.47 square plus 0.47 square to 4.5 ampere. And no load power factor is cos phi equal to IL upon I0, it comes 0.1045. Now coming to the calculation of your block rotor parameters, typically the leakage reactances and resistances. So coming to that, we have to calculate slot leakage, typically the permeance of slot. So lambda SS giving mu 0 in bracket H1 upon 3 WS 2 upon WS plus 2H3 of WS plus W0 plus S4 WS, and keeping the value, it comes 26.3 into 10 power minus 3. And similarly for rotor slot leakage, the permeance, so lambda SR equal to mu 0 with all the same dimensions, so it comes 15.9 into 10 power minus 7. And now coming to lambda SR square, that's a permeance referred to stator. So lambda SCR into K omega square into SS upon K square, K omega square SR. So putting value, it comes 13.9 into 10 power minus 7. So total specific permeance referred to stator is lambda S equal to lambda SS plus lambda SR. So putting value, it comes 40.2 into 10 power minus 7. Now so total slot leakage is X equal to 8 pi F T PH square L lambda upon PQ. So putting the value, it comes X equal to 2.5 ohm, and overhang leakage, typically L0 lambda 0, putting value mu 0 Ks into A square pi G by SS, putting value, it comes 4.74 10 power minus 7, and overhang leakage reactance from the same formula using 8 pi into F T square L lambda upon PQ into X, that comes 2.1 ohm. And zigzag reactance, we calculate from magnetizing XM upon ES upon IS, so it comes 98.4. So zigzag is 5 by 6 XM upon M square in bracket 1 upon QS square plus 1 upon QR square, so it comes 1.92 ohm. So total leakage reactance referred to stator is XS equal to XS, small xs plus X0 plus XZ, it comes 6.52 ohm. And stator resistance per phase RS equal to rho CU into TS into LMTS upon ACU, it comes 1.41 ohm. And total stator plus M is I square RS equal to 536 watt, and total resistance referred to stator is RR dash equal to 4 MTS square KWS square rho in bracket LB upon SR into AB plus 2 upon pi D upon P square into AE, that comes 1.35 ohm. So total resistance referred to stator is R is equal to R small r RS plus RI square, so 1.41 into 1 plus 1.35, it comes 2.76 ohm. Now the total impedance for phase ZS equal to under root S square plus RS that comes to 6.52 square plus 2.76 7.1 ohm. And now the block rotor current is IS equal to ES upon ZS, that is 440 upon 7.162 ampere. And the block rotor power factor cos phi S equal to RS upon ZS, that's putting a value 2.76 by divided by 7.1, 0.389. And now coming to loss and efficiency calculation, so output at the full load is 11 kilowatt, that's 11,000 watt, and sum of losses is 1546 watt, as we have calculated all the losses, and input is now 11,000 plus 1546, so it comes 12,546, and now efficiency is it equal to P upon P in into 100, putting the value it comes 87.7%. Like now coming to stator temperature rise. Temperature calculation, we have to calculate the losses by total surface area, the proper cooling coefficient as given in the table for different parts, and cooling effect, how it is considered with the peripheral speed. You see the cooling coefficient C in middle column of this table. So now cooling coefficient are taken from the table. The outer cylindrical surface of stator core, that is pi d 0L equal to, putting value it comes 0.162 watt meter square, and cooling coefficient for outer surface is 0.033. So inner cylindrical surface of stator core pi dl, and value now comes by the, after putting the value 0.11 meter square, and peripheral speed B equal to pi dns, so it comes 13 meter per second, and cooling coefficient for inner surface is equal to 0.033 divided by 1.0.1 VA peripheral speed, so putting value it comes 0.0143. Now coming to loss dissipated for inner stator surface, so inner cylindrical area divided by C, so 0.11 divided by 0.143, that's 7.68 watt per centigrade. Area of and surface include ducts 0.255 meter square, and air velocity in duct WD into VA, that putting value it comes 1.3 meter per second. So cooling coefficient for ducts CD equal to, putting the value 0.08 to 0.2 into VA, so giving a value of around 0.5 divided by 1.3, it's come 0.115, and loss is dissipated from end surface and ducts is area of ducts divided by CD, so that's a 0.0225 divided by 0.115, that comes 1.96 watt per centigrade. Now total loss dissipation is loss plus, outer loss plus inner loss plus loss in duct, so putting value it comes 14.56 degrees centigrade. So temperature rise theta equal to total loss to be dissipated divided by loss dissipated per centigrade rise of temperature. So putting value is 693 divided by 414.56, it comes 47 degrees Celsius, and has the temperature rise within the safe limit of 50 degrees Celsius, what we have considered initially. Now coming to the subjective questions. What are the main construction part of three-phase induction motor, like stator, rotor, enclosure, and housing? What are the types of the slots used in stator of three-phase, open and semi-closed slot, and what are the effect of presence of harmonic torque in three-phase induction motor? Major physical phenomena are clogging and noise problems. Give the efficiency and power factor of induction motor of different rating. The squirrel cage efficiency of medium rating motors is 0.72% to 91%, and power factor 0.66 to 0.9, and slip ring induction motor efficiency is from 84 to 91%, power factor 0.7 to 92. So this ISC specification says the product of efficiency and power factor should be in the range of 0.83 to 0.88 for the medium power rating. Now coming to the question 5, what are the major differences in construction between squirrel cage and slip ring motor? The main construction difference between squirrel cage and slip ring motors are like squirrel cage, it is of less cost, it has a rigid construction, it produces small starting torque, insertion of resistance into it is not possible. In slip ring it's costly, it has a wear and tear due to the brushes and slip ring. It produces large starting torque by inserting the resistance, inserting of resistance possible in the rotor circuit for control of the characteristics. So what are the to increase the starting torque in a squirrel cage? Okay, starting torque of squirrel cage can be increased by using either double cage or deep bar rotor. Express the range of no load current as a percentage of full load current of three-phase induction. No load current of three-phase induction motor is in the range of about 25 to 40% of full load current. What are the effect of the replacement of copper end ring by brass end ring on the performance of slip ring? Resistance of end ring with the replacement of copper to brass, resulting in a higher winding loss in the end ring, and thereby reducing the efficiency of the motor. To mention the various quality of three-phase induction motor compared to the other electric motor, three-phase induction motor have the following quality in comparison to all electric motor, like it's a more robust, cheaper, and require lesser maintenance. Question level: what is the no load current of induction motor? Why the no load current of induction motor is higher than the of transformer of same rating? The answer is no load current of induction motor is much higher than that of a transformer, with presence of air gap between the stator and rotor and presence of slots in the stator and rotor. Now, question 12: why the starting torque is higher in slip ring? The starting torque of slip ring induction motor can be increased by increasing the rotor resistance, and actual resistance can be inserted in the rotor circuit of slip ring at the instant of starting, resulting in higher starting torque. The actual resistance is finally cut and the resistance rotor winding is short circuited for normal operation. Question 13: how can power factor of induction motor can be improved? The power factor can be improved by making the following changes: reducing the ampere turns per pole, reducing the air gap density, or reducing the length of air gap. Calculate the value of maximum power factor of induction motor if dispersion coefficient is 0.05. So maximum power factor is 1 minus dispersion factor divided by 1%, so it comes 0.905. Why the closed type of slots commonly used in smaller induction motor? The closed slots are used in the following reason: it makes the reluctance more uniform, it reduces the magnetizing current, it improves the power factor, it lowers the tooth pulsation loss, and ensure the quiet operation or reduces the noise and vibration. Why the applicability of three-phase induction motor in industry as a farm sector is more compared to other motor? Application of three-phase squirrel cage induction motor is spread due to following reason: construction is robust, efficiency is good, and maintenance is cheaper, and starting is easy. Now, question 17: why are the large number of induction motor made with the squirrel cage rotors? The construction wise, the squirrel cage machine is robust and require very low maintenance, and this makes it cheaper. Hence, a large number of induction motor are made of squirrel cage rotor. Question 18: state the specific requirement for which wound rotary induction motor is needed. The answer is wound rotary induction motor required for application requiring speed control and high starting torque. Now, question 19: why an induction motor called rotating transformer? The operating principle of induction motor similar to that of transformer. The stator winding is equivalent to primary winding of, and the rotor is winding equivalent to short circuit secondary winding of the transformer. In transformer, the secondary winding is stationary, but in induction motor it can rotate. Therefore, the induction motor is also called rotating transformer. Explain how the slip ring motor is started. The slip ring motor is started by rotor resistance starter. The starter consists of a variable resistance and protection circuit and R start connector. Resistance are connected in slip ring on the rotor. So while starting, the full resistance is included in the rotor circuit to get high starting torque and low starting current, and then the resistance are gradually cut in step. At running condition, the slip rings are short circuit, so the equivalent it becomes equivalent to a squirrel cage rotor. Now, coming to the solved numerical problems. The first numerical calculate the following design information for 30 kilowatt for 40 volt 3 phase 6 pole 50 Hz delta connected squirrel cage induction motor. Calculate the main dimensions of frame, number of turns per phase in slot, and number of stator slot, and number of conductor per slot. So, solution is for considering the various missing data. So, specific magnetic current considering the B average equal to 0.48 Tesla, specific electric loading 26 kiloampere or 1000 per ampere per meter, full load efficiency eta equal to 0.88 and full load power factor 0.88. So, considering the full pitch winding, so with the winding factor KW equal to 0.955. Now, coming to main dimension of stator frame, output coefficient is C0 1.11 pi square KW into B average AC eta into cos phi into 10 power minus 3. So, it comes after putting value 99.2 and synchronous speed of the machine ns equal to 1.2 F by B, it comes 16.66 RPS, and D square product D comes 1 upon C0 Q upon N. So, it comes 0.01815 meter cube, and for best power factor D equal to 1.35 P under root L. So, it comes here solving these two equations. So, it comes L comes 0.17 meter and D comes 0.33 meter. Now, number of stator turn per phase, flux per pole pi equal to pi D upon P, L into B average. So, putting value it comes 0.0141 Weber, and applied voltage per phase is V phase equal to 440 into for delta connection, and considering the induced EMF equal to applied voltage, so stator turn per phase is 4.44 F kW into 5. So, putting value it comes 1.47. Now coming to number of stereo slots, the large number of stereo slots is desirable for the consideration of leakage reaction. However, it results in increased cost and weight of the, hence the considering the above factor, the number of slots per pair page is considered as 3. The total number of slots SS equal to S. This typically 3 into 6 into 3, that comes 54. And number of stereo slot per page SS into M, it comes 18. The number of road conductor per slot, total conductor per slot T conductor equals 6 TS upon M, so it comes 294, and total number of conductor per slot, comes now T conductor by SS upon M, so it comes 16. So hence the revised conductor per page is S upon M into this, so it comes 286, and number of turns revised finally selected T PS dash equal to T conductor by 2, that comes 143. Now coming to second sole example, during the preliminary design of 5 kilowatt 3-phase 4-pole 50 Hz delta connected squirrel cage induction motor, following information have been obtained. Gross length of stator 0.1 meter, stator bore diameter 0.117 meter. Estimated the stator bottom and gross length of 487.5 kilowatt 3-phase 4-pole 400 volt 4-pole 50 Hz delta connected squirrel cage induction motor, assume with the same specific loading as the 5 kilowatt, and missing data maybe should be considered. So synchronous speed of 5 kilowatt motor is NS equal to typically your 2 into 50 by 4 to 25 RPS. So for output coefficient for 5 kilowatt motor C0 equal to Q upon D square length, so it comes 69.2. So design assumption for 5 kilowatt motor is full load efficiency 0.85, full load power factor 0.85, and for full pitch winding factor KW is 0.955. So thus putting value in this equation comes B average into AC equal to 9060. So putting this value, we get a relation B average into AC 90. So specific loading for 7.5 kilowatt come 9060, and design for 7.5 kilowatt with full load efficiency 86 and full load power factor 0.866 and wind pitch factor 0.95. The output coefficient of K dash comes to 70. So for 7.5 kilowatt induction motor D square L equal to, putting the value, it comes 4.28 into 1 power 5 meter, and for best power factor D equal to 0.135 P into DL, putting the value, L comes 0.12 and D comes 0.19. Now D2 square L2, we can keep all the value KW 1 NS1 upon NS2, D1 square L1. So putting the value, it comes 6.8 10 power minus 3 meter cube. Number of poles 6, so ratio comes L upon top 0.51. So thus L upon pi D6 by where it comes 0.51. So L2 comes 0.26 D2, and putting the value of D square L2, this 6.8 10 power minus 3 meter. So we can get the value typically from here, the D cube equal to 6.8 10 power minus 3 meter cube, and D2 comes from this, comes 0.294, and L2 comes 0.078 meter. Now coming to example, solved example third, the stator of 3-phase 30 kilowatt 450 Hz 6-pole squirrel cage induction motor has been designed for 54 slot. The rotor for this motor is designed for the following rotor slot: 36, 42, 46, 47, 48, 52, 53, 45. This is a possible defect in various design, if any, and select the best combination rotor slot. So number of stator slot is 54, number of rotor slot 36. So difference of the stator and rotor slot 56 minus 36 18. In this combination, the difference between the stator and rotor slot is equal to 18. So 3 times the number of poles, thus the clogging and crawling phenomena will be observed with this combination of the stator and rotor slot, hence rejected. Now coming to second combination, number of slot stator is 54, number of rotor slot 42. So difference of these two slots comes around 12. The difference of this is 12. Then 2 times the number of this, so fair chance of the motor develop hook or torque speed characteristic and not desirable. So number of, taking a third option, number of slots equal to stator slot 54, number of rotor slot 46. So difference of these two comes 8, and the difference between the stator and rotor slot is P plus 2. So number of motor will create a lot of noise during the working condition. So hence this combination also rejected for noisy behavior. So now coming to number of stator slot equal to 54, number of rotor 47. So S1 minus S2 comes 54 minus P plus 1. So the effect of this combination of stator slot will be the same as mentioned in third, and avoided. So coming to next combination, stator and rotor 54 and number of rotor 48. S1 minus S2, it comes 54 minus 48 P. So thus this combination of stator slot will be same as discussed, taken and not desirable. Now coming to sixth combination, number of stator slot 54, number of rotor 52. S1 minus S2 is a 54 minus 52. Thus, effect of this will be noisy of the motor, hence avoided. The number of stator slot 51, number of rotor slot for 7th option 53. So S1 minus S2 is equal to 1. So with this combination of stator, motor will be quite noisy and hence rejected. Number of stator 54, number of 45. 1 minus S2 equal to 54 minus 4, 9. This combination of stator will avoid the cogging, crawling, hooks and cups in a synchronous characteristic, and also has the best combination of stator and rotor slot. Now coming to example 4, a 3-phase 3000 volt line, 260 volt, 260 kilowatt, 50 hertz, 10 pole skull cage induction motor gave the following result. During preliminary design, the internal diameter of stator is 35 centimeter, gross length of 35 centimeter, number of stator slot 155, number of conductor per slot 10, assuming the efficiency 90%, power factor of 0.9. Based on the above data, calculate the followings for this skull cage induction motor: total loss in the rotor bar, loss in the end rings, and equivalent resistance of the rotor in terms of. Now coming to with the given data, total loss in the rotor bar will be for the calculation of first the bar current has to be determined. The bar current depends on your rotor slot, and as such the number of rotor slot will be decided to start with. The number of rotor slot equal to number of poles 10 and number of stator slot 1 to avoid the 3 bad effect, cogging, synchronous cups and noising operation. The difference between the number of slot commons will not be equal to 1, 2, 10 plus 1, 10 plus 2, 10, 2 into 10, 2, 3 into 10 into. So considering the above, the number of rotor slots selected for this motor is 115. Now coming to total loss calculation in rotor bar. The rotor bar current per bar is given IB equal to KW1 into SSZ1S divided by KW2 into SR into Z2 to I2. So number of stator slot is 120, number of conductor per slot is 10. So its winding factor is KW1 0.95, number of rotor slots is 115, number of conductor per bar is 1, and equivalent current, rotor current I2 equal to 0.85 I1. So now coming to rotor bar calculation comes with the relation, putting the value of I1 calculating 61.5. So putting the value I bar comes typically 512 ampere. Now coming to sectional area of the bar, considering the current density of 6.5 ampere per meter square because of better cooling of the rotor. So sectional area bar of A bar equal to I bar divided by J bar. So putting value 80.2 ampere per meter square, and length of the bar equal to length of the rotor bar, gross length plus allowable clearance of 5 cm is taken for screwing and the distance between the ends of. So length of the bar is L plus allowances, so it comes 35.5, 35 plus 5, 40 centimeter, that's 0.4 meter. Resistance of bar equal to rho B, RB equal to rho CU into LBR A bar. So putting value 1.05 into 10 power minus 4 ohm. Loss in the rotor bar is total loss in the rotor bar. V bar equal to NR IB square RB. So putting value which comes 3278 watt. Losses in end rings is equal to I bar into number of rotor bar per pole by pi. So it comes 1907 ampere. Losses in end ring, assuming current density again of 6.5 ampere per meter square in the end ring. So considering this sectional area A equal to I upon J, so it comes 293.3 millimeter square. So mean diameter of end ring can be taken 10 centimeters, and the diameter of stator D equal to D minus 10 centimeter, that comes 65 centimeter, and the length of the current path in end ring L equal to 5D 24043.3 centimeter. The resistance of end ring R equal to rho C into LE upon AE. The putting value it comes 1.43 into 10 power minus 4 ohm. Total loss in end rings comes P equal to 2 IE square RE. Putting value it comes 1063 watt. Total rotor losses, copper losses or winding loss P rotor is P bar plus P, that comes 4341 watt, and equivalent rotor current is I2 equal to 0.85 I1, so it comes 52.3 ampere. So equivalent resistance of on stator side R equal to rotor bar losses into 3 into I2 square, so it comes 0.53 ohm. So coming to fifth numerical problems. Following information have been obtained during the design of 3-phase 6600 volt 850 kilowatt 50 Hz 12 pole slip ring motor. Gross length of stator is 45 centimeter. Internal diameter of stator core is 122 centimeter, number of stator slot 144, number of conductor per slot 10, and voltage between slip rings at starting 600 volt, and stator connection present, design efficiency equal to 92%, power factor 0.9. So based on the above information, design of wound rotor of the motor. So diameter of rotor is length of the air gap, L equal to 0.2 to 1 dl, so it comes to 1.68 millimeter. So diameter of rotor is dr equal to d minus 2 lg, it comes to 1.217 meter. So now coming to number of rotor slots, giving due consideration to various coefficient factor, the number of slot per pole per phase is taken as a 3.5. So thus the rotor of slots come yours SR equal to 3.5 into 12 into 3, 126, and rotor slot pitch comes torr equal to pi dr upon SS, so it comes 0.0303, and number of rotor turns comes voltage at starting between slip ring 600 volt. So with the star correction of stator winding, the stator voltage per phase is VL upon root 3. So it comes like typically your 6600 by root 2, so 3810. So now considering the ES equal to 3810, winding factor for the rotor winding can be assumed equal to the stator winding, KWS equal to KWR, and total number of stator conductor T conductor into SSR, that's a 10 into 140, so 1440, and the stator turns per phase is now TS equal to SS upon M into T conductor by 2, so it comes 240, and then rotor number of turns comes TR equal to ES up ER upon ES into KWS upon KWR into TS. So putting the value like a 600 by root 3 upon 3810 into 1 into 40 is comes 22, and rotor conductor per phase is T conductor 2 into TR 44, and rotor slot per the SR upon M, that comes 126 by 3, that's 42. So now rotor turns per phase TR equal to 22, rotor conductor per phase is T conductor 2 TR 44, rotor conductor per phase is SR upon M, that's a 42. To accommodate number of conductor in 42 slot, so conductor per slot is 1, and 44 conductor to 44 conductor to 42 conductor converted to modify value of turns per phase TR dash equal to 1 into 21. So rotor current is now with given efficiency of 92%. So input power to the motor P in equal to P upon P efficiency, it comes 9 to 4 kilowatt, and full load power factor 0.91. So stator full load current comes from IS equal to P in upon 3 EPH into PF, so it comes like 88.8 ampere, and equivalent rotor current IR equal to 0.85 IS, so it comes like a 75.5 ampere, and rotor current IR equal to KWS into SS into ZS divided by EG KWR SR ZSR into IR, it comes like 863 ampere. Now full load power factor is your 0.91, so stator full load current per phase IS it comes IS equal to 8.8, equivalent rotor current is your 75, and rotor current is 863. So dry rotor conductor size is your current density is taken 5 ampere per millimeter square. So cross section area of the rotor bar is AR equal to IR upon JR, so it comes your 172.6 millimeter square. So now the size is so large that the conductor stand is 4 rectangular strips, each of 43.15 millimeter square in parallel. Standard size of rectangular strip selected 11 millimeter into 4 millimeter. So and sectional area of standard rectangular strip is 43.1 mm. Thus the sectional area of rotor conductor 43.1 into 4, that is 172.4 millimeter square, and the size of rectangular strip is with insulation is 11.5 millimeter into 4.5 millimeter, and this is typically found for the size of selection is considered 11 millimeter width with the thickness of typically of your 43.4. So that's a standard selections for the rotor bar. Now coming to 4 rectangular strips are arranged in the rotor slot, 2 strips with widthwise and 2 strips depthwise. So with this arrangement, the size of typically rotor slot is depth of the slot. The space by conductor 2 into 11.5 23. The slot line 3 into 1.5 4.5, slackness 3.5, wedge 1 millimeter, lip is also 2 millimeter. So total typically depth comes 34 millimeter. Similarly for the width of the slot, space occupied by the conductor 2 into 4.5, that's a 9 millimeter, slot lining 2 into 1.3 millimeter, and slackness 1 millimeter. So total width comes 13 millimeter. So now coming to mean turn length of the conductor LMT equal to 2L plus 2.3 tau into 0.08. So putting value, it comes 1.72 meter, and the resistance of rotor winding per phase R2 equal to rho CU LMT at TR upon A conductor. Putting value, it comes 0.0044 ohm, and copper loss in the rotor winding is PCUM I square R. R2, so it comes 9831 watt. Now coming to the sixth numeric example, find the magnetizing current of a 2.2 kilowatt 3-phase 450 hertz 1500 synchronous speed discal cage induction motor having a full load efficiency of 0.8 and power factor 0.825. The machine is to be started by start delta starter. Assume suitable and justified value of remaining design data. So coming to synchronous speed, it's ns equal to n upon s. So it comes 25 rps, and poles are 2f upon s. That comes 4. Assuming average flux density of 0.44 Tesla, 1 ampere conductor length 21,000 and winding factor 0.955. So kVA input Q equal to P upon N into eta into power factor, so it comes 3.33 kVA. Now coming to output coefficient, C equal to 1.11 pi square kW into P average into AC. So putting value, it comes 97. D square product comes CQ upon C0 NS, so it comes 1.375 10 to power minus 3 meter. And for a low cost design, L upon 2 should be between 1.5 to 2. So taking L upon tau 1.5, so putting the value of L upon tau 1.5, you get a relation L equal to 1.18 D, and putting the value in the above relation of D square L, so we get D equal to 0.105 meter, L equal to 0.125 and tau equal to 0.0825 meter. Now coming to stator voltage per phase, that is given 400 volt for delta connector winding. A flux for phi m equal to B average at tau into L. So this comes 4.54 10 to power minus 3 Weber. Stator turns per phase comes Ts equal to E upon 4.4 F pi P into Kp. So this comes 416. Taking a slot per pulse per phase equal to 2. So stator slot is M into Q into P. Putting values come 24, and stator slot pitch IS comes putting a value 13.75 millimeter, and total stator conductance 60 S, that comes equal to 2496, and conductor per slot is ZS equal to 2496 by 24, that comes 104. So mass winding is tapered semi-closed slot is used in stator. So mass winding is single layer winding, and the total number of stator coils is equal to the half of the stator, so that's a 12. So coil span CS equal to slot per pole, so SS upon P, that's a 24 by 4 6. So but the coils will not be an even integer in case of mud winding, therefore span is 5 slots is used. Thus the coil are chorded by 1 slot pitch. So angle of chording alpha equal to 1 by 6 into 180 30 degree. So pitch factor becomes like Kp cos alpha by 2, that's a 0.966, and distribution factor for slot 2 Kd equal to sin sigma by 2q sin sigma by 2q. Putting value, it comes 0.96. So stator winding factor Kws equal to Kd into Kp. Putting value, it comes 0.933. And conductor size calculation now for this calculation of your stator current is Is equal to P upon 3S into Pf into efficiency. So putting value 2.77 ampere, and stator line current is root 3 Is, that comes 4.8 ampere. Now taking current density 4 ampere per meter square, so area of stator conductor is Js equal to Is upon Js, so it comes 0.6925 millimeter square, and diameter of bare conductor comes 0.94 millimeter. So nearest D is 0.95. The area of the stator conductor used is S equal to 2 pi D square by 4. So putting value 0.709 millimeter current density for stator conductor. Delta sigma is Is upon As, so it comes 3.91 millimeter. So and the diameter of enameled copper is D1 equal to 1.041 millimeter. Now coming to slot dimensions, the space required for bare conductor in slot is ZS equal to S. So putting the value, it comes 73.6 millimeter square, and taking a space factor of 0.4 for slot. So area of the slot, each slot is S equal to ZS into S into space factor. Putting value, it comes 184 millimeter square. So before deciding the slot dimension to give the above area, the minimum slot width that keep the flux density within the limits should be found. So maximum flux density in the teeth is required is 1.57 Tesla. So minimum width of the teeth is your pi m upon BTS by P into T. So it comes 3.9495 millimeter square. So now taking a dimension, taper dimension of this with the given here in the figure, and slot at the bottom, for the relation pi d plus 2 into wedge plus slip plus 2h upon ss minus ws minus pi gh upon by 12. So putting the value, virtually it comes your 8.88 pi h upon by 12 area of the conductor portion of the slot comes here with our half h 8.88 pi dh by pi. So it comes 184 millimeter, or h it from this comes 17 millimeter, as you can see in the diagram. So now coming to straight design, so a tooth of constant width of 6 millimeter is taken. So suppose h is to be height of in millimeter as shown. The dimensions of the slot are worked out as under. Take a lip of 1 millimeter, edge of 3 millimeter. The slot width a is pi in bracket pi into d plus 2 wedge plus slip plus 2h upon h minus wts. Putting a value, it comes 8.88 millimeter. Now coming to 4 slot dimension, width of that the bottom is 8.88 pi h upon 12. So it comes 13.2 millimeter as according to the diagram, and depth of the slot is h plus wedge plus slip, it comes 21 millimeter. The arrangement of conductor and the insulation are shown in the length of mean turn LMT shown in figure, and mean turn length is now LMT 12 plus 2.3 tau plus 24, it comes 0.68 meter. Now flux density T comes pi upon SS by P into W2 into Li. So here it comes 1.12 Tesla. Bt is, but this is within the limit. So for now coming to calculation of stator core, flux in the core phi core equal to phi whole by 2. So putting value, it comes 2.27 into 10 power minus 3 Weber. Assuming the flux density of 1.2 Tesla for the core, the area of stator core is ACS equal to pi core upon B core. This comes 1.89 10 power minus 3 meter square. Now depth of the stator core DCS ACS upon Li, so it comes 16.8 10 power minus 3 meter, and taking a core depth of 17 millimeter. So flux density stator core BCS equal to DCS into 1.2 divided by DCS. Nu, it comes 1.18 Tesla. So outer diameter of stator and DO equal to D plus 2 DCS plus DS. So it comes 118 millimeter. And now coming to rotor design, first we have to calculate the length of air gap, so that rotor diameter can be calculated. So it comes length of the air gap equal to 0.2 under DL in millimeter. Putting value, it comes 0.43 millimeter. Air gap is large, therefore LG normally preferred for small rating motor 0.3 millimeter. Taking a then diameter is dr equal to d minus 2 lg, so it comes 104.4 millimeter. Now coming to for selection of rotor, typically rotor slots calculation. The number of rotor slots is chosen such that the smooth starting and accelerating condition are obtained. This is occurred by adopting a one slot less than the one slot more per pole per pair. So in the rotor, so taking a rotor slot per pole per less than 1, the number of rotor slots HR equal to SS minus P by 2, this comes 22, and rotor slot with YSS pi into D minus 2 LG by SSR, so it comes 14.9 millimeter. Now coming to calculation of rotor bar, so current density in each bar is I equal to 2 MTKWS into TS into I cos phi. Putting value, it comes 244 ampere. Assuming current density of 6 ampere per milliliter square because of better cooling in the rotor bar with a high strength, so area of the each bar is AB equal to IB upon JB, and it comes 40.7 millimeter square. A bar of rotor bar of 6.5 millimeter and width of 7 millimeter deep is used with the area of 40.7 millimeter square. Now coming to looking at figure as a dimension, so area of the bar is AB equal to 6, with this 44.6 millimeter. So dimensions of the rotor slot are width of the slot VSR equal to 6.8 millimeter and depth of DSR equal to 9.3 millimeter. So before forging the flux density in the at the root of rotor teeth must be assessed. So slot which has the rotor teeth is pi DSR minus 2 DSR by SR. So this comes 12.2 millimeter, and tooth of the width of that comes slot with minus WSR, that's come 5.4 millimeter. So flux density at the root comes phi m upon SR upon T into L upon WT, it comes 1.36 Tesla in the limit. Therefore the MF required for rotor loss will not be excessive. The bars are skewed one slot per pitch to avoid the slot harmonics and noise and vibration, and cogging. Excessive bar by 115 mm beyond the core length on each side, taking a 10 mm as the increase in length for skewing. The length of each bar is with skewing LB equal to LR plus 2 into 15 plus 10 mm, so it comes 165 mm 0.65 mm meter, and resistance of bar is then RB rho Cu into LB upon Rb. It comes like 77.7 10 power minus 6 ohm. Total copper loss in the bar is Pb equal to SR into Ib square Rb. So it comes 101 watt. Now coming to entering calculus, the entering current is I equal to SR Ib upon pi P at 428 ampere. Taking current density of 6 millimeter ampere per milliliter. Area of bar is I upon Je. So it comes 71.3 millimeter square. Using an end ring depth of 10 into 8 millimeter. So depth of the ring is D equal to 10 and thickness is RET equal to 8 millimeter. Area of the ring provided A equal to D into T, 10 into 8 into 10 power 18 millimeter square, and mean diameter of hand ring D equal to 75.8 millimeter. Distance of each hand ring rho R equal to rho Cu into D upon 8, so it comes 62.5 10 power 6 ohm. So copper loss in the two end rings is P equal to I square Re. It comes 23 watt. Total copper loss in the rotor Pb upon Pe, that's 124 watt. So we have rotor copper loss upon output S upon minus S. So from here slip at full load comes 5.6%. Now coming to rotor core, depth of the rotor core is taken as equal to the stator core. So area of the flux density in the rotor are same as the stator. So depth of the rotor core comes TCR equal to 17 millimeter, and inner diameter of rotor laminate pi r, dr minus 2, dsr minus 2, dcr 51.8 millimeter. Now coming to no load current calculation, that is typically a magnetizing current. So MF required for various parts. All 5 parts are calculated here. Air gap for air gap for stator. For that we have to calculate contraction factor. So for stator we have to have slot opening upon gap length. So that is 2 upon 0.3, that's 6.67, and corresponding to this ratio Carter coefficient is 0.68 from the graph, and gap contraction for stator slot KGS comes YSS upon YSS minus KCS into W0. It comes 1.11. For rotor, slot opening upon gap length comes 1.5, 1.35, and typically the MF required for rotor, it comes slot opening upon gap length equal to 1.5 by 5, corresponding Carter 0.6. Go to gap contraction factor for rotor slot KGS are equal to YSR divided by YSR minus KCR into W0. It comes 1.064, and gap contraction for rotor slot KGS is equal to KGSS into KGSR equal to, putting value it comes 1.18, and KGD equal to H1. There is no rotor duct present. So now coming to total contraction factor KG equal to KGS KGD, it comes 1.18. The equivalent length of air gap comes kg LGS equal to kg into LG, it comes 0.354 millimeter, and flux density air gap at 60 degree from interpolar BG 61.36 B average, that comes 0.6 Tesla. And now MF for air gap comes ATG into 8 to power 800,000 into BG and ILGS, putting value it comes 170 ampere. Now coming to MF calculation for stator teeth. The width of the stator teeth 6 millimeter, WTS 6 millimeter, and of the teeth is ATS equal to ATS SS upon WTS and LI. So it comes 4.05 10 to power minus 3 meter square. Plug density BTS is 1.12 meter square. So BG 60 is 1.36 into BTS. This comes like typically 1.52 Tesla, and corresponding to this plug density from the material property, MF per unit length is ATS 1200 meter per 1200 ampere per meter. So MF required for stator is a capital ATS equal to small ATS into GCS. It comes 25 ampere. Now coming to MF calculation for stator core, area of the core is ACR DCS into LI, come 1.9195 into 10 power minus 3 meter square. Plug density in the stator core BCS 1.85 millimeter. So corresponding to this plug density, MF required ATS small ATS 280 ampere per meter. The length of the path of the stator core LCS equal pi d plus 2 SS DCS by 3p. So LCS comes 40. Putting value it comes 43 into 10 power minus 3 meter. I have required for stator cores capital 8 into TCS into LCS, that comes 12 ampere. But for road, now coming for rotor teeth MF calculation, so WTR is 6.3 mm. The area of the rotor teeth per pole SR upon L into WTR, it comes 3, putting value 3.9 into 10 power minus 3 meter square. And flux density in rotor teeth at 1/3 I, BTR 5 ATR it 1.16, and BTR 60 now is 1.36 into BTS, it comes 1.575 meter. And corresponding for material property, this flux density per unit is 2000 ampere per meter. If required for rotor teeth is ATR equal to small ATR into DSR, it comes 19 ampere. For now coming to calculation for rotor core, from the previous calculation, area of the core is ACR equal to 3.15 Pi 1 into 10 power minus 3 meter square. So flux density in rotor core is BCR equal to 1.185. The MF per meter is 80 CR from material property 280 ampere. And length of the magnetic path in rotor core is LCR equal to pi d minus 2 SSR 2 GSR by 3P 18 millimeter, and MF required for this total 80 CR equal to TCR into LCR, that is putting value 5 ampere. Now to coming to for calculation of magnetizing current for all 5 parts of magnetic air gap, stator, rotor core. We have calculated area, we have calculated length, we have calculated flux density, we have calculated BG60, and then is MF per unit for different material, and then followed by total MF. So 80, 60 comes 231, and magnetizing current comes here. I am equal to 0.427 P into 80, 60 by kWs into S. It comes 1 ampere. And these are the references what we have followed for this lecture. If any question is, I will be happy. Thank you very much.